Enthalpy of reaction. It is the heat evolved or absorbed during the reaction when number of moles of the reactants gets completely converted into products. Okay. It is the heat evolved or absorbed in a reaction when number of moles of the reactants gets completely converted into products. It is represented as delta H or delta H of R. Okay. And it depends upon the condition at which the reaction is carried out. In a standard state of condition, standard state means in pure form and 1 bar pressure, standard condition, it can be represented like this. Okay, standard state, the reaction can be represented like this. Now, delta H of R in a reaction, in a chemical equation, it will be equal to sum of the enthalpies of the products minus sum of the enthalpies of the reactants. Okay. So, enthalpy of reaction will be equal to sum of the enthalpies of the products minus sum of enthalpies of the reactants. Let us take an example. Methane plus 2O2 gives carbon dioxide plus 2H2 in this reaction. So, enthalpy of reaction will be equal to delta H of R will be equal to the enthalpy, sum of the enthalpies of the products. So, here molar enthalpy of carbon dioxide plus molar enthalpy 2 into molar enthalpy of H2O. Sum of this, okay, minus sum of enthalpies of CH4 gas plus 2 into enthalpy of oxygen gas. Okay. This will be the delta H of R. So, delta H of reaction will be sum of enthalpies of products minus sum of enthalpies of reactions, of reactants. So, molar HM represents molar enthalpy. Okay. Next, there are different types of enthalpy of reactions like enthalpy of combustion, enthalpy of formation, enthalpy of solution, enthalpy of atomization, etc. First one, enthalpy of combustion. It is denoted like this. And standard state, it can be represented like this at standard condition. So, what is enthalpy of combustion? The enthalpy change accompanying the complete combustion of 1 mole of a substance into its in excess of air. So, 1 mole of the reactants gets converted into products in excess air. Okay. Enthalpy change accompanying the complete combustion of 1 mole of a substance in excess air. Okay. and it is represented like this. At standard condition, it is represented like this. Next, second one, enthalpy of formation. Represented as like this, and standard enthalpy like this. Okay, so enthalpy of formation means the enthalpy change accompanying the formation of 1 mole of compounds from its constituent elements. Okay, enthalpy change accompanying the formation of 1 mole of compound from its constituent elements. Okay, and the case of elements, standard enthalpy of formation of elements are 0. Standard enthalpy of formation of elements are 0. Okay. Next, third one, enthalpy of solution. Represented like this, enthalpy of solution. Okay. So enthalpy change when 1 mole of solute or substance dissolved in a specified amount of solvent. Enthalpy change when 1 mole of a substance dissolved in a specified amount of solvent. So this may be exothermic or endothermic. Next, fourth one, enthalpy of atomization. Enthalpy change when 1 mole of substance dissociate into its gaseous atoms. Okay. Fourth one, enthalpy of atomization. Can we represent delta H of A. So 1 mole of the substance, enthalpy change. Enthalpy change when 1 mole of the substance dissociates into its gaseous atoms. Okay, for example, CH4 gas gets converted into carbon atom and hydrogen. Okay, gets converted into its gaseous atom, and delta H is found to be 1665 kilojoule monoverse. Okay, this much energy is absorbed during the reaction. Next case, enthalpy of phase changes. Enthalpy of phase change. So, phase transformation also requires energy. Okay, so first one is standard enthalpy of fusion. Okay, so conversion of 1 mole of solid substance into its liquid at its melting point. So, enthalpy change during the conversion of 1 mole of a solid substance into liquid at its melting point. Okay, let us take an example. H2O, ice, that is H2O solid, in the solid state it is ice at 273 Kelvin. It gets converted into liquid, H2O liquid. Okay, and delta H of fusion is found to be plus 6 kilojoule mole inverse. Next, standard enthalpy of vaporization. Standard enthalpy of vaporization. So, here the enthalpy change during the conversion of liquid into vapor at its boiling point under that is standard case. So, it is under standard pressure, that is 1 bar pressure. Okay. So, enthalpy change during the conversion of liquid into vapor. Liquid into vapor at its boiling point. At its boiling point at standard condition, that is at 1 bar pressure. That is example H2O liquid. Boiling point is 373 Kelvin. Gets converted into H2O gas, that is steam. Delta H of vaporization is represented like this, which will be equal to plus 40.79 kilojoule mole inverse. Okay. Next, third one is standard enthalpy of sublimation. Here, the enthalpy change during the conversion of solid directly into its gaseous form at standard condition. Enthalpy change during the conversion of 1 mole of solid directly into its gaseous form at standard condition, that is 1 bar pressure, and at standard state, that means 1 bar pressure and standard temperature. Okay, for example I2, solid gets converted into iodine, gets converted into its gaseous form. Here the sublimation is taking place. Okay, so delta H of sublimation, standard condition, delta H will be equal to plus 62.4 kilojoule mole inverse. This will be the value for delta H, that is energy absorbed during the reaction. This much heat is absorbed during the reaction. So, for example, in the case of solid, this is in the case of iodine, solid carbon dioxide. Solid carbon dioxide at 193 Kelvin standard temperature, 195 Kelvin at standard temperature, delta H is found to be 25.2 kilojoule mole inverse. Next, another case, in the case of naphthalene. Case of naphthalene also, sublimation is taking place and delta H is found to be 73 kilojoule mole inverse. 73 kilojoule mole inverse. These are some examples of sublimation. Next, in the case of enthalpy of reaction, in the case of enthalpy change, it depends upon the intermolecular force of attraction between the substances undergoing phase transactions. So, in the case of acetone, what happens? Acetone, the intermolecular force of attraction is very less. So, the sublimation takes place easily. So, weak dipole-dipole interactions. But in the case of water, what happens? There is strong hydrogen bond. So, intermolecular force of attraction increases. So, enthalpy change is more in the case of water than in the case of acetone. Okay. Next. We can write delta H of sublimation will be equal to delta H of fusion plus delta H of vaporization. Okay.